Test on Monday. Format is typical for me. We got nomenclature of alcohols and ethers. Yeah. We have reactions of alcohols and ethers, including epoxides. Multi-step synthesis, largely using epoxides. Yeah. What else do we have? Oxidation of alkenes, NMR. We will see a comprehensive spec problem, such as in the workbook, and any other topics we've covered. There will be some multiple choice questions, but also largely a short answer like quizzes. Any questions about the test format? Okay, let's continue with aromaticity. Any questions thus far about what we looked at on Wednesday? Aromaticity. Okay, I think we can look at the green sheet largely today. And we have another definition of aromaticity. Actually, it may be pretty similar to what we've seen before. Aromatic versus anti-aromatic. Okay? Benzene is a very stable molecule, unusual reactivity. Hopefully we got that stated last time. What about this? What about this compound? It's a cyclic compound. Would you expect it to be aromatic? Well, why do you expect this to be aromatic? Why do you say that's aromatic? Every atom has a p orbital and they're all conjugated. Cyclic conjugation of all p orbitals. What about that? Is it cyclic? Yes. Does every atom have a p orbital? Yes. Are they all conjugated? Yes. So would you expect that to be aromatic? So far, based on definition, it turns out that it's actually not so aromatic, not so stable. This compound is not stable. It will actually dimerize at very low temperature, even at very low temperature. Not a stable compound. You cannot bring this compound in here and say, hey, I've got this liquid here, or most likely a liquid. So what's the difference? Actually, this compound is known to be anti-aromatic. Anti-aromatic. Now, both are fully conjugated systems. But why is this one so stable, yet this one is not? That's what we have to get to. And we can have our working definitions. Aromatic, and an unusual stability due to full cyclic conjugation around the ring. Anti-aromatic is an unusual instability due to full cyclic conjugation around the ring. But why? And this will really get us at looking deeper into aromaticity and, at the same time, anti-aromaticity. Remember in Organic 1, we often said that conjugation is a good thing? Usually is always a good thing. And I told you, there will be one exception, kind of. Well, with the anti-aromatic compound, conjugation is actually a bad thing. So why? By the way, what do you want to call this compound? We know this is benzene. What do you want to call the compound on the right? More of a systematic name. What do you want to call this compound? 4 carbons, butane, but it's 2 enes, so it's butadiene. Well, that's 4 carbons with 2 enes, but it's cyclobutadiene. Okay? Pretty straightforward name. That name is written there. Okay, we need to learn how to do MO diagrams. Molecular orbitals. All right? Let's first start with the MO diagram of butadiene. Now, lot of times MO diagrams are just sort of glossed over in Gen Chem. Did y'all do any MO in Gen Chem? You did? Good. Did you do MO diagrams? Did you take Gen Chem here?
Yes, I did. So I go with Dr. Juan.
Okay. Okay. Likely you may have did some MO diagrams. Good. Anybody else do MO diagrams? Yeah, in Gen Chem? Yeah? So you can do an MO diagram of that molecule there? Okay, in my organic one, I don't do any MO diagrams. We didn't do any. Okay? We could have with UV vis. Actually, with UV vis, I may have mentioned it. We had excitation to higher energy levels. And where did those come from? Okay. All right. First thing is, how many p orbitals here? And we're doing the MO diagram of the p orbital system. How many p orbitals? 4 p orbitals. How many pi electrons? And how many electrons in the p orbitals? Right, 4 pi electrons, okay? We have to know that. That's what we're working with. And this is going to lead to 4 molecular orbitals. We'll just sort of put everything up here and we'll kind of talk about it as we get to it. You'll say, well, why? And then we'll back up and explain why. But the 4 MOs here are going to look like this here. In terms of energy levels, okay? Energy. And the midline is going to cut right through here because the midline cuts through symmetrically between your energy levels. And this is 4 molecular orbitals. Okay? What is a molecular orbital? Well, what is an atomic orbital? An atomic orbital is an orbital that's on an atom, and they have different shapes, and we call them maybe an S or a P. But we can also hybridize atomic orbitals and have an sp3 hybridized atomic orbital. But what is a molecular orbital? An atomic orbital is spread over one atom, and a molecular orbital is spread over the entire molecule. Can you imagine an orbital spread over the entire molecule? It's a little, it takes you to have to think about that. And why that can be first very odd. All right? But that's what it is. Because once we have conjugation, it really becomes one system. You've heard me say that before? That one system has orbitals spread over the entire molecule. What do these orbitals look like? Well, to get at that, one way to get at that is to draw the overlap. I'm going to come down here. I got to sneeze. Maybe not. Okay, you got p orbitals here. These can interact how? Ultimately, there's 2 ways for orbitals to interact. They can interact constructively and kind of build upon each other, or they can come together and interact destructively and sort of cancel each other out. This is like sound waves, or waves in a lake of water. The waves come together and build a bigger wave, or that would be sort of in phase terminology. Or they can come together out of phase and it'll go dead, and each wave will get canceled. Okay? Same thing with sound waves. Sound can amplify, or you can actually have sound come together and you have spots where there's no sound. Sound can get canceled. Yeah? ultimately with this here is these four orbitals can theoretically interact in four different ways. One way is for them to all have the same phase. If they all have the same phase, they're all interacting. Okay? That's top and below. I'm just going to do top, but we know they fully interact side to side. Okay? And that's the best way they could theoretically interact. And this is, that right there is now one orbital. Really? Is it really one? It looks like it's four. Is this one or four? This is four atomic orbitals all interacting at the same time to make one molecular orbital. Once they start interacting, they're no longer individual atomic orbitals. It becomes one. It's almost kind of like hybridization, where an S and a P mix, and you make an SP, but that's still an atomic SP hybrid. This is where different atomic orbitals interact to make one big orbital that we call a molecular orbital. And it has energy that sits very low. Okay, what are other ways that these could interact? I wish I'd have drawn this a little bit over. I could move that over here. Another way for them to interact is, I'll go ahead and do this quickly. Instead of drawing the orbitals, can I just draw signs? Another way for them to interact would be plus, plus. Now I'm going to actually draw the orbitals. We need to do that a couple of times. Then we'll move to doing just signs. Plus, plus. But what if we call that minus and minus? What if these came together and interacted like that? You would have overlap here, okay? Overlap there, and you'd have overlap here. Well, constructive overlap is what I'm saying. But what do you have between these two original atomic orbitals?
Destructive.
Destructive. And because it's destructive, we're going to say that there's actually like no sound there, no wave there, no electron density here. And what do you call a region or a plane where there's no electron density? Who said that? Very good. It's called a node. Yes. Now, which situation looks better? My lower one or my upper right? Yes, all overlap is lower, is better, lower energy. Okay? Oh, by the way, I wish I had, okay, now I see, I should have drawn this just straight above. Because we're going to have 1, 2, 3, 4. How do we know that? One thing is, as we go up, number of nodes increases. 0 nodes. I'll put this here. Okay? 4 MOs. 0 nodes. 1 node. And that's that one. Guess how many nodes this is going to have? 2 nodes. And this is going to have?
3.
Yes, that's easy. That's what it's always going to be. Okay, I'm not tall enough to draw above that. So maybe it is good that I drew it to the side. Because the next one, and we can get rid of this right here. Let's see if we can draw another one. And it's going to be higher in energy than that one. How many nodes?
2.
2. One way to a helpful way to do this is to start with drawing 2 nodes. And the 2 nodes are going to be symmetrical. Let's have one here and one here. Now, since we see this as a node, If this is plus, what is going to be the phase over here? Minus. Thus leading to the node that we drew. And now I'm not going to draw in the orbitals, because I did that a couple of times. Anytime I do it, there's really an orbital here, and I'm showing the phase of the p orbital. Now, what is this phase here?
Minus.
Do we have a node between these two carbons? No, so that's minus, same phase, so they're overlapping constructively. When there's a node, so this is what? Okay. And this has two nodes. There's more other terminology we can use here. How many bonding interactions are shown here in this MO? Bonding interaction, bonding interaction, bonding interaction. 3? Okay. I want to get rid of this 4 MOs. That's the whole thing. 3. 3 bonding interactions. Okay? Let's do this. Let's call it 3 bonding net. 3 bonding net. What is the net up here? 1 bonding, 2 bonding. But what do you call this here? Let's label it like this. This is called bonding. This is called bonding. Well, what do you want to call this here? It's called antibonding. What is the net here? 1 bonding cancels out 1 antibonding. What are you left with? 1 bonding net. Okay? What type of interactions do you have up here? What is this interaction? Antibonding. What about here? Bonding. And what is this? And what's the net here? Antibonding cancels a bonding. What are you left with? Yes. And one thing that is always the case is when you're below your energy midline, these are bonding molecular orbitals. Bonding net, bonding net. When you're above, these are going to be anti-bonding molecular orbitals. But the two below are not equal because one has 3 bonding, one has more bonding interaction than the one that only has 1 bonding net. Okay, if you got some room on your paper, you can draw it up there. I'll draw the 4th one here. How many nodes for the 4th one?
3.
It's going to be boom, boom, boom. All these are nodes. If this is plus, what is this?
Minus.
Minus. If that's minus, what is this?
Plus.
And if that's plus, this is?
Minus.
And what's the interaction here? Anti-bonding, and this is? Anti-bonding, and this is?
Antibonding.
And what's the net?
3 antibonding.
3 anti-bonding net. You see how that's the worst? Meaning it's the highest in energy? Yes. Now these are the 4 MOs of butadiene, the molecule we're looking at. Now, these are orbitals. Now we put our electrons in. How many electrons do we have?
4.
4. We had it here. How do you put them in? Aufbau principle, Pauli exclusion principle, Hund's rule. The same way you put it into a ground state configuration. 1 here. Where's the next one go? Here. Then where? Here. And the 4th one? There. There's your MO diagram for butadiene. 2 electrons sit in this MO. What is an MO? Okay, it's a molecular orbital. It's an orbital. This is 1 orbital here. Because once they mix, it's no longer 4 atomic orbitals, it becomes 1 thing. It's 1 orbital, if you can believe that. And how many electrons sit in an orbital? 2. Got 2 sitting in this one. I got 2 sitting in this one. And then these other MOs are empty. This is largely based on a lot of the high-level math. A lot of high-level math that comes into this theory. Okay? Linear combination of atomic orbitals, I think, is sort of the heading of that math. Okay? There you go. Does this look familiar to anything you've seen before? Okay. Now, the fact that we understand that you have these higher energy orbitals, we can talk about, like in UV vis, how we excite an electron. And one of these electrons can be excited to a higher energy orbital. Okay? All right. Now let's do an MO diagram of benzene. Questions while I'm erasing? How many p orbitals in benzene?
3. Or no.
How many p orbitals in benzene?
6.
Six p orbitals. How many pi electrons?
6.
6 pi electrons. How many molecular orbitals are we going to make? 6. Okay, 6. Those 6 are going to look like, not this. Damn. These 6 are going to look like this. Midline will run right through the center here. Okay. The thing with benzene, because it's cyclic, we're going to have degenerate molecular orbitals. Okay, degenerate. I'll try to do the 6 here. Six p orbitals. I'm not going to draw the actual orbitals. What's the best way for these 6 to interact? Same phase, all 6 having the same phase. Any nodes here? No node. Okay. Zero nodes. Okay. That's what that means. That's the best way. Let's try another way. We're moving up a level. How many nodes here? 1. Okay. There's 2 different ways to draw a single node. One way is to have it right here. And if this is plus, what is this? Plus and plus. If that's plus, what is this? Minus, minus, minus. And you see the node through there. Because it's a ring, cyclic, there's another way to draw one node. And it's like doing a math problem and you got 2 answers. And the other node is right through here. Actually right through 2 carbons. Can you imagine two carbons and neither one of them having any electron density? Well, that's what that kind of is. Okay? And if this is plus, what is this? Plus. And this over here. See, these are not even interacting. You could say plus and plus, but actually it would be minus and minus, so we can kind of keep things symmetrical. But there's not even any electron density on the upper and lower carbon. What's the net for this guy? 6 bonding net. What's the net for this on the left?
4.
Bonding, bonding. What is that? So we got bonding, bonding, anti-bonding, bonding, bonding, anti-bonding. What's net? 2 bonding net. What about this over here? What's its net? That's all you got, right? What's the net?
2.
See? Both of those are 2 bonding net. That's why they sit at the same energy level. And they're called what? Degenerate. Orbitals that have the same energy are called degenerate. So there's 3 MOs. Do you see how they're all bonding MOs? Bonding net. They're going to be below the energy midline. Okay, let's draw 3 more total. How many nodes for this one?
2.
2 nodes. 2 nodes can come like this. There'll be 2 nodes. And if this is plus, what is this? Minus, and what's this? Minus, plus, minus, minus. So what if all 6 interacted that way? If they interacted this way, what would be the net? Anti-bonding, bonding, anti-bonding, anti-bonding, bonding, and what? What's the net? 2 anti-bonding net. Those above the midline are going to be anti-bonding molecular orbitals. And there's actually another way to get one like this. And that is to draw it through the carbons and through here. And if this is plus, that would be minus. There's no overlap here. I'm going to call this one plus, and since that one's plus, I call that minus. What's the net there? All you got is 2 anti-bonding. But see, it's the same as the other one. Both of those are 2 anti-bonding nets, same energy. Now the 6th one we're going to draw at the top, but I'm going to draw it over here. How many nodes for this one? 3. How can we get 3 nodes? I think it would be here, here, and here. No. Let me see if I can get 3. For some reason, these markers are a lot better. Is this going to be,
Yes.
if this is plus, that's minus,
Plus.
plus, minus, plus, minus? Yes. And what's the, if you go around here, what is your net interaction?
Six anti-bonding.
How many?
6 anti-bonding.
Yeah, 6 anti-bonding net. 0 nodes, 1 node, 2 node, 3 nodes, is that right? Okay, there you go. Here are your 6. There's the energy of your 6. How many electrons do we have to put in here? 6. 1, 2, 3. After here, where do you put the next one?
The next.
What does Hund's rule tell us? You feel degenerate with 1 each first before you start pairing up. 5 and 6. What do you see for benzene? What do you see here? First off, all electrons paired. I agree? That's a good thing. Secondary to this is all electrons in what type of molecular orbitals? Bonding MOs. That's what we have here. Now, of the two, that's the first thing. That's the most important. That's the first thing. The second thing up there is secondary and will not always hold true for good stuff. All electrons pairs is the main thing. But you do recognize that all electrons are in bonding molecular orbitals, right? Okay. Now let's do one for cyclobutadiene. This guy here. How many p orbitals in this system? How many pi electrons?
4.
Yeah. So far, these have been equal. Soon, this number will not be equal. Okay? How many molecular orbitals we're going to have for this?
4.
Yeah. 4 molecular orbitals. That's always consistent. If we had 10 p orbitals, how many MOs would you make?
4.
There you go. Okay. This is going to end up with 1, 2, 3, 4. We can just go ahead and say that. Why? And I like to draw these. Draw it, right? If this is plus, how many nodes for the first one?
0.
0. That'd be the interaction all the way around. And what's the net bonding here?
4 bonding.
Yeah. 4 bonding net. Okay. Now this has how many nodes? The next one? 1. If this is plus, what's this? Plus, and that's plus. This is minus and minus. Look at this. What's the net bonding here?
0.
You've already determined it? But I see it's It's zero bonding net. Bonding, bonding, antibonding, antibonding. So, is this a bonding molecular orbital or an anti-bonding molecular orbital? Zero net. And we call that a non-bonding molecular orbital. And guess what? Where's the energy midline here? Symmetrically through here? Those that are on the energy midline are going to be non-bonding. We can get another one like that, a degenerate one, by putting the node here, call that plus and minus. What's the net interaction there? Why zero? Because there's nothing. Is there any bonding? No. Is there any antibonding? So what do you want to call that type of MO? Non-bonding. There you go. One node, right? 0, 1. How many nodes for this one?
4.
How many nodes for the top one? 2 nodes. Put one here and here. If that's plus, having minus, plus, minus, what's the net here?
4.
Everybody here with me? 4 anti-bonding net. Okay, all these have energy. Okay, I'm not putting every single thing up here. There are your 4 MOs. How many electrons we have? 1, 2, 3, and 4. There you go. So what do you see for cyclobutadiene? Are all electrons paired? No! It's actually, what do you call something with an unpaired electron? Yes, a radical, but this is not 1 but 2. It's a diradical. And that's why it's not stable. It's very unhappy. That molecule will want to dimerize and change even at very cold temperature. The MO diagram, the MO explanation helps us see that. Okay? You got 1 electron sitting in this orbital, molecular orbital, if you can really wrap your mind around what that means, and 1 electron sitting in that molecular orbital. And it's not a happy camper. I'm never going to be able to bring in cyclobutadiene and say, hey guys, look at cyclobutadiene. It won't exist. Okay? Now it looks like it could be just a diene. It's worse than that. We call it anti-aromatic. What is the definition of anti-aromatic? As a result of cyclic conjugation, which often leads to stability, this has led it to be what?
Unstable.
Highly unstable. It's led it to be a diradical. This brings us to Huckel's rule. We'll do other compounds, such as we did 6 and 4. This is 4 p orbitals. We'll do some with 8, 10, 12, 14, 16, 2. We'll go ahead and state Huckel's rule. Huckel's rule, a chemist, says that a cyclic conjugated pi system with 4n plus 2 electrons will be aromatic. But a cyclic conjugated system with 4n electrons will be anti-aromatic. And here, n is just an integer, some number. Basically, with each integer, what is 4n plus 2? If n is 1, what is 4n plus 2? 6. And 6 would be what? Benzene? benzene has 6 pi electrons. Yes, Huckel's rule predicts benzene would be aromatic. What if N was 2? What would this number be? 10. A cyclic conjugated system with 10 pi electrons will be aromatic. That's what Huckel rule tells us. What if N was 3? 14. 6, 10, 14, 18, if you keep going, those all should be aromatic. Which should be anti-aromatic? Well, what if N was 1? 4. N was 2? 8. 12. 4, 8, 12, 16, those should be anti-aromatic. What if N up here was 0? 2. You can have some aromatics with just 2. That would be where N equals 0 in Huckel's rule. Okay? Where does Huckel's rule come from? It just comes from the fact that as we do more, whenever you have 4n plus 2, and you do an MO diagram, you're going to see they all going to be paired. But whenever you just have 4n pi electrons, you're going to end up with a diradical. Again, we'll have to cycle back and forth on here. This will make more sense as we move forward. Okay? What about other compounds? We've done 4 and 6. What about that one? How many pi electrons here? 8. Well, based on Huckel's rule, should it be aromatic or anti-aromatic? Anti-aromatic? Yes? If it was anti-aromatic, how would you expect it to behave?
It would be unstable.
Very unstable. Do you think that you could go to the lab and maybe distill it and then just kind of be happy? No. Cyclobutadiene, you cannot do that with that one. So you would not expect this to be a stable compound. Can we do instead of just relying on Huckel's rule, can we do an actual MO diagram of this? Okay, I'm going to do it sort of quicker and shorter, and we'll go from there. Anytime you do these, there's always one good MO at the bottom. The best would be where they all interact like plus, 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 plus all the way around. There's only one way to do that. Always just one at the bottom. And from there, you go 2 at a time until you run out, until you get all 8 up there. So there's 1. 2 more. Then we can come back with 2 more. And how many is that? 5. And what is that? 7. And then this would be just 1 at the top for a total of 8. How many nodes here?
0.
How many nodes here?
1.
Yeah? If you were asked to draw some of these, could you do them? Starting with nodes and coming up with plus minus around? For example, one node, if there was no here, you could maybe draw a node and then go plus, 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 and then minus, 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 minus. And you'd have all overlap, except for right here. And then you can add up bonding versus anti-bonding. Where's the energy midline? It's going to cut symmetrically through in terms of energy. Right now, just symmetrical. The energy midline is here. So what type of MOs is this? Bonding MO? Bonding MO? What is this? Anti-bonding MO? Anti-bonding MO? What are you going to call these two on the midline? Non-bonding MOs. Okay? how many electrons we have to put in here?
8.
1, 2, 3, 4, 5, 6, 7, 8. What do you see? Diradical. But Huckel knew that already. Huckel told you it would be diradical. That's what Huckel's rule is based on, because Huckel knew that every time you did this with multiples of 4, you're going to get a diradical. 4, 8, 12, 16. Do it. It's always going to be a diradical if you do it this way. But guess what? If it's 4 and plus 2, those numbers, which are 2, 6, 10, 14, 18, anytime you do those, you're going to end up paired. Huckel realized this and stated his rule. Okay? What do you see here? Not only is it a diradical, but the 2 electrons are sitting in what type of orbitals? They're not even in bonding orbitals. They're non-bonding. That's even second, worse again. Does this compound look like a happy camper? No. But it is though. Okay, here's the problem. That's a very stable molecule. The theory tells us it should not be. I didn't bring a model today. Didn't know we would get this. This compound is actually non-aromatic. Because this compound is not planar. Let me ask you this, guys. Do you think a compound wants to be anti-aromatic? No, it does not. That's a very unstable thing. Nature doesn't like to be unstable. If it was planar, okay, this is very important. Don't forget this part. It first has to be cyclic conjugated pi system. All p orbitals interacting. That implies that it has to be planar. Okay? All right? Benzene is planar. Okay? And each carbon has a p orbital sticking up. Imagine, okay, there's 4 p orbitals. Imagine there's 2 more for a total of 6. They're only going to be like that if the system is planar. If the system is bent, like down, it's going to make one of the p orbitals do this. And it would no longer be cyclic conjugated. Okay? It has to be planar for them to, okay? So, does this want to be cyclic conjugated and thus anti-aromatic? No. So what happens is the 2 ends of this molecule actually just go boop, and then goes boop. Okay? I don't want to be anti-aromatic. And right there it's like, yay, I'm no longer anti-aromatic. Game over. I'm just a happy tetraene.
How are you supposed to look at the paper and know that?
Do I?
How are you supposed to just know that molecule?
Good question. Very good. That gets us to experimental evidence. Okay? First thing is, understand that this is always based on it being planar. If it ain't planar, then that don't apply. How do you know? Experimental evidence. I'm telling you that this compound is very stable. You can distill it. You can react it. Now, if it was aromatic, we could maybe do some experiments on it. And we'll talk about that when we do an example there. Where when we do Huckles, it looks like it's aromatic. Okay, we'll answer that question moving forward some. Okay, for Wednesday after the test, please have tried some of these others. And move ahead with this handout, because we'll pick up the pace here and we'll start applying what we've been talking about. Okay? And we'll do MOs of cations and anions. Ions. Have a good day, guys.
Didn't want
You can come this afternoon if you want.